I can stand wherever pretty much. All right. All right. Thank you. We're really excited about our new technology. My name's Ed Faden. I'm from MacMod Analytical. MacMod Analytical is a distributor of analytical supplies to the pharmaceutical industry and a variety of other industries. And we have a new product that we brought on called Evosphere. And Evosphere is a monodisperse particle technology. So I'll go on to describe what that means. So when you look at particle technologies in general, when most vendors say that their particle size is 3 micron, what they really mean to say is that it's an average of 3. So, some of the particles in there might be 2.2, 2.4, 2.6, 3.2, 3.4, and so on. With this new technology, it's called monodisperse. So the particle size distribution has gotten significantly narrowed. And I'll go on to describe why you would care about that, but it is a really big advantage. And then we also test this for lipids, which is some really exciting data. So this is just going on to say that it's a chemical process, not just a flour sifter that they just sifted out the small and the little guys. They specifically designed this with a modified Stober process to come up with a particle size that is uniform throughout the column. So why do you care about this? You have to harken back to the Van Deemter equation. And when you look at the Van Deemter equation, you're kind of trying to look at the physical properties of the column. So there's the A term, B term, and C term. Now, so the A term is the thing that's most impacted here with this new technology. So essentially, it's how the analytes travel through the interstitial space in the column, the space between the particles, not in the particle, but between the particles. So this term in itself is become so optimized with this new column. So this is what you get as a result, right? So what's the quickest path from 2 points? It's a straight line, right? And so when analytes go through this column, it goes through in a straight line versus where other vendors have a more polydispersed column and it's sort of more of a circuitous. So what happens as a result? The bands that come off the column are extremely tight. So what does that mean for you? Very, very tight and efficient peaks. So you get 60% higher efficiencies. So I think that you could look at this technology as the 2 main pillars of chromatography right now in liquid chromatography are core shell technology, which you guys might know as solid core, core shell, follicular shell, Porous shell. All the vendors do it. And then there's fully porous, right? Ours we would view, and it's very, very new, it's only about 2 or 3 months old. Ours we would view as kind of the marriage of both of those technologies with none of the disadvantages of either. So the disadvantage with core shell technology is that it's a very, very highly efficient column. But the problem is with core shell is that essentially you can't load very much onto the column. So if you have something in the analytical scale that you wanted to load more onto the column because it's in very low abundance, it's very hard to do on core shell because it overloads versus this column, which is giving you core shell-like efficiencies, but on a fully porous particle. So we came up with a new phase here, Evosphere C12. So a lot of you have heard of C4s, C8s, C18s, but not many have heard of C12. So why is C12 cool? It's actually more hydrophobic than C18, which is kind of counterintuitive. Most people would think it goes C4, C8, C12, C18, right? But you can actually bond more C12s to the surface of a particle than you can C18, which in effect creates a more hydrophobic environment for the analytes to interact in. So we use this C12 technology. I sent it out to one of our collaborators at the University of Florida, Tim Garrett, and he tested our C12 column in a 3 micron format against the Waters BEH C18 1.7 micron and a C8. And the main thing I'm trying to do here is 2 pieces. One, does ligand length, C8 versus C12 versus C18, what's the ideal length for lipids, right? What is the length that's going to be the best peak shape, the best idea for using for lipid analysis? And then the second piece, does monodispersity, this uniform particle size throughout the columns, does that play a role? And what we found is that the results are, this is the first time I'm actually talking about it, but the results are really, really exciting. So again, the top one is the water's BEH 1.7 micron. The bottom one is an ACE C8 3 micron. So I compared a polydisperse to our monodisperse. So again, I'm exploring, does monodisperse matter? What's the optimal ligand length? And use normal parameters to test it. Don't mess with all this stuff like normal lipid analysis. Is it going to come up with better results? So this is our, experimental conditions, very typical stuff. 98.2 IPA, acetonitrile water in the B, 500 microliters per minute, 50 degrees C, and it's a multi-step gradient that looks like that. So, as you would expect, with a 3 micron, you're getting half the back pressure of the 1.7. That's not too exciting, but it is a benefit, right? So 3 microns, half the back pressure. So this is what we got. I'm going to center in on each one of these and compare them to the water's BEH C18 and the C8. So I got the lyso-PCs, the phospholipids, and the phosphatidylcholines, and then the cholesterol esters and triglycerides. So what is the data? You're looking at a 3 micron here in a C12 against the water's 1.7 micron up here, and you're getting sharper peaks, less tailing. That's huge. Same thing, same story here. More tailing on the waters, way less tailing on the evosphere, and it gets better as the data goes on too. So for cholesterol esters, you can see how much tighter these peaks are on a 3 micron versus a 1.7. And what I found out basically is that the C8, not so great for lipids. So I really centered in on C12 versus C18 because those seem to be the most usable. Again, every single thing here on the phospholipids, look how big of a difference this is between the water C18 and our C12. Same thing here, same thing here, same thing here. Way less tailing, much better peak shape, very, very reproducible. This is next to the C8, and like I said before, the C8's on the right, C12's on the left. C8 just doesn't do what we want it to do. So C8's not that usable for lipids. You need more hydrophobicity than that. Now this is phosphatidylcholines with different levels of unsaturation. So the colon 5 is the number of double bonds, essentially. And you can see just all the way through the line. I mean, this one's a huge one. I mean, look how much better that looks than that. It's a big, big difference. And we're talking about a 3 micron. Again, C8, same thing against the C12. It's just not very usable. Again, triglycerides, right? 3 microns, and look how much better and tighter the 48.2 triglyceride is than this broad one versus the water's BEH C18 1.7. It's a big, big difference. Triglycerides with 52 total carbons. I mean, the top trace is pretty stark. This one versus that. I mean, that's pretty huge. Look how much tighter those peaks get. Again, versus the C8, not much utility to the C8. We don't see, the peaks are just so much thinner on the C12, and just overall, I'd recommend the C12. And then this final one, 52.3. This is getting pretty big as far as, lipid goes, triglyceride 52.3. And you can just see that the tailing on the 1.7 versus ours, how much thinner this peak is. So really you could, and we have this column available in a 1.7 as well. So you could imagine how much better it could even get if you were to go to a 1.7, right? So this is on a 3 and it's beating a UHPLC column, which is huge. This is the TG envelope, so it's just going to show that the MS is working properly. So that's the only reason that this slide is in here. This is the new set of columns. If you come by our booth, you can come see them. I can talk to you about it. They're available in the capillary all the way up to analytical and then up to prep too. So we have them available in the 21.2 millimeter ID columns as well. And in conclusion, the Porous Evosphere is an innovative technology. It's great for lipid analysis. C12, we really centered in on as the ideal ligand length for this type of analysis. And then in the 3 micron particle size, it's performing even better than sub 2, which is a huge benefit. So again, just take it back to what's monodisperse, same particle size all throughout the column. It's the marriage of the fully porous and core shell with none of the disadvantages of either. And C12 in a 3 micron is a really, really great column for lipid analysis. So thank you.
Thanks, Ed. Any questions in the room? No. Christian, anything online?
No, there are no questions in the Q&A.
Okay.
Yep. There's other C12s, what we've seen, but the only one that's put it on a monodisperse particle technology. And the monodispersity has played a huge role in the efficiency uptick that you're getting specifically for lipids. So, we still got to do more tests to see if it's the monodispersity or the ligand length, but what we've overall seen is it's a combination of both. And the combination of both of those for lipid analysis has been a really big contrast. And from what we're hearing all over the industry is that this column seems to be a bit of a different